We can take another example to understand sp2 hybridization. Let us take the example of C2H4, that is ethene molecule. Here carbon will undergo rearrangement of atomic orbitals in such a way so as to form 3 sp2 hybridized orbitals and one of the orbital remains in the unhybridized state. Now when these two carbon atoms combine with each other and with the hydrogen atoms, the formation of ethene molecule takes place as follows. So this is one carbon with its 3 orbitals, hybridized orbitals, lying in the trigonal manner. Similarly, for the second carbon, if these are the hybrid orbitals lying in the trigonal manner, the overlapping takes place with the hydrogen orbitals in such a manner. Two hydrogen orbitals of two different hydrogen atoms combined with the orbitals of sp2 orbitals of carbon. Similarly, in the second carbon also the same thing takes place, while one of the sp2 hybridized orbital of one carbon combines with second hybridized orbital of another carbon, and the unhybridized orbital of carbon lies at an angle of 90 degree, that is in perpendicular plane to the hybridized orbitals, and it leads to the formation of pi bond. Rest of the orbitals lead to the formation of sigma bonds. So in this molecule we can say we are having 5 sigma bonds, out of which 4 are formed due to carbon-hydrogen overlap and 1 is formed due to carbon-carbon overlap. And in this molecule we have 1 pi bond that is formed due to the lateral overlapping of unhybridized orbital, p orbital. Now the molecule can be represented as follows. Carbon forming one bond with another carbon and 4 bonds with 4 different hydrogen atoms, and the pi bond can be shown in the form of electron cloud lying above and below the plane. This is all about the sp2 hybridized orbitals or sp2 symmetry. Next is sp hybridization. It involves intermixing of one orbital of s subshell and one orbital of p subshell, leading to the formation of 2 sp hybridized orbitals. These two sp hybridized orbitals orient themselves at an angle of 180 degrees to each other so as to have minimum repulsion among them. This hybridization is also known as diagonal hybridization. The shape of the orbital is, the s orbital is combining with one of the p orbitals giving it the shape like this. This is s orbital, this is p orbital, and this is the hybridized sp orbital. Let us see the example of formation of BeF2 molecule for this. The ground state configuration of Be is 1s2, 2s2. Let us see the outermost shell configuration. In 2s, we have two paired electrons, while there is no electron in the 2p shell. But in the excited state, one of the 2s orbital electron gets excited to 2p orbital, leading to the configuration of 1s2, 2s1, 2p1 can be represented like this, forming the hybridized orbitals like this. Since only two orbitals are taking part, hence it is 2sp hybrid orbital formation. Now when these two sp hybrid orbitals combine with 2p orbital of fluorine, the configuration we have already seen. Fluorine is having one electron unpaired, and this unpaired electron undergoes pairing with the unpaired electron of sp orbital of Be, leading to the formation of BeF2 molecule. This structure could be shown like this. This is the beryllium Be hybrid orbital. It is undergoing overlapping with p orbital of fluorine as follows, leading to the formation of 2 sigma bonds. Next type of hybridization is sp3 dehybridization, where intermixing of 1s, 3p and 1d orbital takes place. It is intermixing of s, 3p orbitals, px, py and pz orbital along with one of the d orbitals, say dz square. These all intermix to lead to the formation of sp3 hybridized orbitals. And the shape of the resulting hybrid orbital is like this. In this we have three orbitals which are called equatorial orbitals, and two orbitals are called axial orbitals. E stands for equatorial and A stands for axial. The three equatorial orbitals lie at an angle of 120 degree to each other in one plane, while the two axial orbitals lie perpendicular to the equatorial orbitals. Let us understand this hybridization by taking the example of, say, PCl5 molecule. Phosphorus having atomic number 15 has the configuration 1s2, 2s2, 2p6, 3s2, 3p3. Since the outermost shell electrons take part in the bonding, so we will see the arrangement of electrons in the 3s and 3p orbitals. It is 2 electrons in 3s and 3 unpaired electrons in 3p are present, and no electron is found in 3d subshell in the ground state. But in the excited state, one of the 3s electron gets excited to the 3d orbital and leads to the formation of 5 sp3d hybridized orbitals. These 5 sp3d orbitals combine with vacant orbitals of chlorine atom, leading to the formation of sp3 dehybridized molecule. In the case of chlorine, we can see atomic number is 17, configuration is 1s2, 2s2, 2p6, 3s2, 3p5. In 3p subshell, one of the electron is unpaired, and this unpaired electron undergoes pairing with the electrons lying in the sp3d orbitals of phosphorus. Next hybridization is sp3d2 hybridization. Here, 1s orbital combines with 3p orbitals and 2d orbitals to form sp3d2 hybridized orbitals. And the number of such orbitals is 1 plus 3 plus 2. That is 6 sp3d2 hybridized orbitals are formed. And these 6 hybridized orbitals can combine with unpaired electrons of any of the 6 atoms, or 6 electrons, unpaired electrons of any of the atom. Like example we can take of SF6. Similarly, next hybridization is sp3d3, where 1s combines with 3p orbitals and 3d orbitals, resulting into total 7 sp3d3 hybridized orbitals. Example we can take of IF7 molecule. This is all about the concept of hybridization. Now next topic is dipole moment. Dipole moment is represented by mu. Dipole moment is generally seen in polar covalent compounds. That means such type of compounds where the atoms undergoing sharing of electrons have some difference in the electronegativities. That means electronegativity of A is different than electronegativity of B. Such a compound is known as polar covalent compound. Now in such compounds, the two charged ends of the bond, they behave as electrical dipole, and their degree of polarity is measured in terms of dipole moment. Let us again understand this thing by taking the example of HCl molecule. In HCl, HNCl undergoes sigma bond formation by the sharing of electrons. But as we know, chlorine is more electronegative than hydrogen, so it will try to attract the shared pair of electron more towards itself, and hence it will get a partial negative charge and hydrogen will gain a partial positive charge, due to which a sort of electrical dipole is seen in the molecule. This dipole is measured in terms of dipole moment. It can be defined as the product of magnitude of charge of any of the atoms, any one of the atoms, and the distance among them, distance between them. So we can say mu is equal to E multiplied by D, where E stands for the charge and D stands for the distance. The unit of dipole moment is dBi, represented by capital D, and 1 dBi is equal to 1 into 10 raised to the power minus 18 ESU centimeter, or it is equivalent to 3.335 into 10 raised to the power minus 30 coulomb meter. The direction of dipole moment is from positive atom to negative atom, and it is shown with the help of a symbol, that is an arrow pointing from positive atom to the negative atom and with a vertical line at one end. So for HCl molecule, we can show the dipole moment like this: HCl dipole moment pointing from H to Cl, where H having partial positive charge and Cl having partial negative charge. The importance of dipole moment is that the molecules which have dipole moment, they are called polar molecules, and the molecules which do not have dipole moment, they are non-polar molecules. Example H2, Cl2, etc.